Hello everyone, so this is Nabinina from University of Siegen. So in this video I'm going to show how we can use this specific component, which is the time-triggered extension layers for the TTELVersalNoC, and I will also show the simulation and the hardware implementation of these components. So this is the agenda for this video. I'm going to show how we can set up the Versal board, and then we can import the DTL code on the video too. After that, I will generate the block design of the time-triggered TTELVersalNoC and simulate it, and finally implement the design on VCK 190. Start. Hello everyone, this is Nabinina from University of Siegen. In this video, I would like to show all the equipment which we used for the demonstration for the time-triggered extension layer for the TTELVersalNoC. So this is the VCK 190 that we used. So at the moment we can see that this is already like GTEC mode, so we can start using this board now. So I'm going to turn on the FPGA board. When we turn on this, we can see on the terminal that it's here running the system controller, as you can see on the video. So it will take a little bit time. Start. Yeah, so we can see here that the system controller is done, as you can see on the screen here. So I'm going to program our FPGA. So here we have a simple program like hello world. So I'm going to program this on the VCK 190. Go in here and then run as launch hardware. So let us see. So you can see over here that we are programming the board. Here also. See, so we can see these errors, and these errors is due to our board. If you can see in this board, in order to program the FPGA, all of this LED, this or the power code should be turned on. So here it's not turned on, so we are going to run a command on the system controller to turn on this LED. So I will go on the system controller command. So first, I will type the XAT. Stop. Yeah. So this is the command that we need to type on the terminal. So I will start with the exit, and then you will type the enter and tab. So now we need to run the command. So this is the command that we need to use to set up the right voltage. So now if you see the FPGA, we can see that all of the LEDs are turned on. It means that we can now program our FPGA. So I'm going to program our FPGA with a simple application hello world. Here, as you can see, so I'm going to run it like launch hardware. So as you can see here, this is successful because we can see the print, which is hello world, successfully run hello world application. So now we are going to continue for the slide for the demonstration. Thank you very much. So I'm going to import the code and start with opening the Vivado. So the first thing that I need to do is to create the project. So we can select the location in which we want to put our project. Now we can import our RTL code. So I will add files and locate it in the code location. Here we have two libraries, which is the safe powers and systems. So I'm going to add those both library. After adding the library, I need to change the name of the library for systems and safe power. Here we are using the VCK, so I'm going to select the VCK 190. We have imported the code for TTL, and here we have two TTL, which is TTL0 and TTL2. The number of TTL is configurable, so we can easily configure the number of the TTL. It can be like 3, 4 or n. Depends on the design. So now I am going to change the path in which we are using our configuration file for the schedule. So we need to locate the path in which our schedule is placed. So now everything is fine. It's time for packaging the IP, so we can create and package a new IP. So since we already have our code, we can use the current code. So before we will review and package our IP, we can, for example, change the name of the IP based on what we want, but here I just use a TTL as a reference. And finally, I'm going to review and package the IP. And now, after importing the code, I'm going to create a block design for the TTELVersalNoC using the previous TTL which we have packaged. So we know that we are using the VCK 190. And then I'm going to add the IP in which we have just packaged. So I need to set up the location of the IP so I can use it. After creating the block design, we can use a pre-existing IP from the Xilinx. For example, we use the chips here. That's include the different processors. And after that, we can run the block automation. and set up the PL clock and reset. And here I'm using the DDR. After that, we can, for example, open the Versal chips to modify any configuration what we want. So we are using the PMC, and now I'm going to activate the AXI. So here you can see that AXI is added, and now I'm going to add my TTL code, TTL IP. So here we can see that the TTL is connected to the AXI which I just added. And here we are using the GTB, which is the global temp based used in the TTL. So this is the clock used here to inject the, for example, the messages. Now I'm going to configure and increasing the slave. So here it means that all of the slaves are accessing the port, and we have these two ports, so we can connect the TTL with the TTELVersalNoC. And I also had the two more clock, since we have two more slave. So when we run the block automation, the TTL is visible for the S06, and again S07 can see the TTL also. So now the Versal chips is connected to the TTELVersalNoC through the time triggered extension layer. So now we can inject the messages to the TTELVersalNoC according to the predefined time. And now we are going to add the GTP, which is a global time based. So we need to connect the GTP output with the GTP of the TTL, and the reset also, low reset with the low reset from the reset Versal chips. And here for the micro tick, we need to add a PL clock. So here the clock for the TTL, we are using the 100, and for the global temp based, for the micro tick, we use 2.1 megahertz. So this micro tick clock can be changed based on the granularity which we want. So here we just use the 2.1 megahertz. So I'm just unassigning the address and assign it again to make sure that all the addresses are fine. After that, we can validate the IP to see if something's wrong. So here there is a problem because of the QoS. So I'm going to modify it on the QoS and use bandwidth as 100, because there is a maximum that we can use. So this is the reason of the error that we got. After that, we run again the validate design. So hope there will no errors again. Yes, so we can see that it's just a warning because of the interrupt that we have, but it won't affect the functional behavior of our design. So yeah, I will just like connect it to the constant value, which is 0, to remove this warning. And then we forget to connect the reset of the TTL and validate again. So now all the warning will removed. So now, as we can see here, that we can see all of the communication on the VersalNoC and the different quality of services that we have just selected. So I can generate the output product and then like having also a wrapper for this design one. So for generating the wrapper, it will take a little bit times. So I'm going to skip the process. So yeah. So after generating the block design, we are going to simulate the time-triggered VersalNoC to see the functional behaviors of the entire system. So here we are just use the two custom core, the core 1 and the core 0. The core 1, which I highlighted, and the core 1 is connected to a pass-through and then going to the TTL, and again going to a pass-through, and after that connected to the network on chip. So we can conclude here that the NOC and the cores, we have an interface which is the TTL. So here we have these test bands that we have developing to inject the messages to the VersalNoC. So here, as I mentioned, that we have the two core 0 and the core 1, and the both cores are injecting the messages to the VersalNoC at the same time. So when we inject the messages at the same time using the same resources, of course there will be like a delay because the one core need to wait and the second core need to wait. But using the TTL, we can avoid the conflict of messages. So based on the schedule is responsible that we only inject the messages to the VersalNoC when the resources is free. So this can be used to reduce the jitter. So now here we can see here that we have two TTL 0 and TTL 1, and the both TTLs are accessing the DDR. So I'm going to run the simulation. So now the core 0 and the core 1 are injecting the messages to the VersalNoC at the same time, but due to the TTL, the messages won't reach the VersalNoC at the same time, because the TTL will only inject the messages according to predefined time. So here we can see that this is the messages for the first TTL 0. So we are injecting all of those messages. If you see on the DDR, we can see that we are receiving the messages from the TTL 0. And if we focused on the TTL 1, we can see here that the TTL1s are also injecting the messages according to the predefined times to avoid the collision of the two messages from the core 0 and the core 1. So we can see that the TTLs are injecting the messages to the VersalNoC, and it's also reached the DDR. So now we can see that the functional behavior of the TTL is working very well, and using the two core to illustrate the behavioral functionment of the time-triggered VersalNoC on the simulation. So after simulating our design, everything seems working. Now we are going to implement our designs on FPGA. So we are going to use the VDIS. Since we already have the XSA files, we're just going to use it. So this XSA file is the entire designs for the time-triggered VersalNoC, and to see if we can, for example, communicate through one core to another core, we just use the single core to write the messages and read the messages, and see if the messages that we are writing from the let's say the source core is received by the DDR, and we can also read this from the same core. Yeah, so here we have the hello world. Since I already have my code for testing the VersalNoC, I just copy it and paste and use in this example to illustrate the time triggered VersalNoC. So those library, we don't need those, so I just remove it and build the code. So here we can see that each TTL has an address, and we can write the messages to each TTL through the specific address. So I'm going to open the port USB 1 to see the messages executed on the car. So here I'm sending the messages from one car and reading the messages from the same cars. So here, when we run the, for example, when we configure the FPGA using our bitstream, we should see that we receive the messages when we send the messages. So now I'm going to configure the Versal platform with our bitstream. So simple word, program the FPGA. So here the error is due to some voltage problems on the Versal board. So we need to configure the voltage of the power good using this command. And now when we program the FPGA, there should not be an error again. So here we can see that we are receiving the messages. So the TTL is working very well according to what we designed.